Have you ever actually stopped to think about how a computer, a machine that fundamentally only understands on and off, ones and zeros, can calculate something as massive as the weight of a galaxy or as tiny as the width of a single atom? It's kind of wild, right? We just take it for granted that our digital systems can effortlessly juggle these massive scientific quantities and unbelievably tiny fractions. But beneath the surface of all that code, there's a hidden, beautifully complex hardware reality. So in this explainer today, we're going to unpack exactly how computers pull off this mathematical magic trick. Okay, let's dive into our roadmap for today. We'll start with the fixed point problem, then look at how floating point representation comes to the rescue. From there, we'll break down the anatomy of a float, walk through encoding both a positive and a negative number, and finally, zoom out to look at precision and the big picture. All right, let's kick things off with part one, the fixed point problem. To really appreciate the genius of modern computer arithmetic, we've got to look back at early digital math. And at the absolute center of this is something called the radix point. Now, in our everyday base 10 math, you probably just know this as the decimal point. But in the broader world of number systems, radix point is the universal term. It's basically the anchor. Numerals to the left are your whole numbers, and numerals to the right are your fractions. In early digital systems, engineers used what's called a fixed point number. And, true to its name, once the hardware designer decides where this radix point lives within a string of bits, it cannot be moved. It is permanently locked in place. Seeing this conceptually brilliantly illustrates the mechanics, and honestly, the fatal flaw of that fixed approach. Positional weights in binary work a lot like decimal. Just like decimal goes ones, tens, hundreds moving left, binary goes ones, twos, fours, eights. And to the right of the radix point, we get halves, quarters, eighths, and so on. It's super straightforward, and it actually lets us use standard integer arithmetic circuits. But if that radix point never ever moves, we've got a massive problem. If you need to calculate tiny microscopic fractions, you're literally wasting all your whole number bits. On the flip side, if you're calculating the distance to Jupiter, you waste all those fractional bits. It leads to incredibly suboptimal memory use and severely limits the actual range of values you can encode. Which brings us to part two. Enter floating point representation. Computer engineers desperately needed a way to break free from that rigidity. The solution? Let the point float. Instead of a static, unmoving radix point, floating point representation dynamically shifts the radix point based on a location value encoded right inside the number itself. If you've ever used scientific notation in a math class, writing 3 times 10 to the 8th power, instead of writing out 300 million with all those zeros, you already understand the core concept here. Floating point representation is basically just binary scientific notation, tailored perfectly for computer hardware. To make this work, the computer takes a number, converts it into binary scientific notation, and then slices it into 3 distinct fields to be stored in memory. First up, it encodes the sign. Is the number positive or negative? Second, it encodes the exponent, which tells the computer exactly where to float that radix point. And finally, it encodes the mantissa, which holds the actual core digits of the number itself. Let's look a little closer in part 3, Anatomy of a Float. Back in the 1970s, different CPU manufacturers handled floating points in completely different ways, which created an absolute nightmare for software developers. So in 1985, the IEEE 754 standard was introduced to make everything interoperable. We're going to focus specifically on the 32-bit version. It's officially called binary 32, but you'll almost always hear it called a single precision float. It takes exactly 32 ones and zeros and divides them into 3 strict territories. You get exactly 1 bit for the sign, 8 bits for the biased exponent, and 23 bits for the mantissa. Let's see what that actually looks like in practice. Now, what's really interesting about how this is laid out is an incredible space-saving hack engineers designed into the mantissa. Think about it. When you write a number in normalized binary scientific notation, it will literally always have a single 1 to the left of the radix point. Always. The creators of IEEE 754 realized, hey, if it's literally always a 1, why waste a precious bit of memory actually storing it? So they just drop it. That whole number 1 is just implied by the hardware. This brilliant little trick actually gives engineers an extra bit for fractional precision, completely for free. The exponent field also has a very clever trick up its sleeve. Exponents can be positive or negative, right? But dealing with negative numbers in binary usually requires a complex system called 2's complement, which just makes hardware math a lot harder. IEEE 754 sidesteps this entirely by using a biased exponent. We just take the original exponent and add 127 to it. This shifts the entire scale, ensuring that the 8-bit exponent field only ever has to store positive unsigned numbers. When the computer reads it later, it simply subtracts that 127 biased to get the real value back. It's so elegant. All right, let's put this into practice with part 4, encoding a positive number. Okay, enough abstract theory for a minute. Let's actually see how your computer takes a standard decimal number, like positive 22.125, and squishes it into a 32-bit float. The computer executes a clear, totally predictable algorithm every single time. It converts the decimal to a fixed-point binary number, normalizes it into scientific notation, and then calculates our 3 fields: the sign, the biased exponent, and the mantissa. Finally, it just concatenates them all together. Let's watch this math play out step by step. Here we go. First, 22.125 becomes 10110.001 in binary. Next, we normalize that by floating the radix point 4 spaces to the left, which gives us 1.011001 times 2 to the 4th power. Now for the 3 fields. It's a positive number, so our sign bit is a crisp 0. Our exponent is 4, and when we add our 127 bias, we get 131, which in binary is 100000011. That's our exponent field right there. Finally, the mantissa. Remember that awesome hack? We drop the leading 1. We take what's left after the radix point, which is 0110001, and we plop it right into the mantissa field. Since that field strictly requires 23 bits, we just pad the rest of the empty space on the right with trailing zeros. Combine them all, and boom, you have your 32-bit representation of 22.125. Pretty wild to see all those bits come together, isn't it? Now, let's look at part 5, encoding a negative number. Let's move on and see how this builds, because that last example was super clean, since 22.125 terminates perfectly. But our hardware has physical limits, right? So what happens when we tackle a negative number that has a repeating fractional pattern? Let's encode negative 45.4. Right out of the gate in step 1, we hit a snag. The fractional part, 0.4, doesn't translate cleanly into binary at all. It actually turns into an infinitely repeating pattern of 0110. But the process remains exactly the same. We shift the 0.5 spaces to normalize it. Because it's negative, our sign bit is now a 1. Our exponent is 5 plus our 127 bias, giving us 132 for the exponent field. Now for the mantissa. We drop the leading 1 again, grab the fractional part, complete with its endless 0110 repeating pattern, and we just start filling in the 23 bits. Once we hit that 23rd bit, we are physically out of memory space in a single precision float. So the hardware just chops off the rest. That infinite pattern literally just ends. Which leads us perfectly into part 6, precision and the big picture. That abrupt chopping off of data we just talked about is a great lens for understanding the big picture. When we chopped off that repeating fraction a second ago, we permanently lost a tiny bit of precision. A 32-bit single precision float gives us roughly 7 significant decimal digits of accuracy before little errors start creeping in. Now, for video games graphics, that's usually totally fine. But for calculating the trajectory of a multi-billion-dollar spacecraft, yeah, not entirely good enough. That's exactly why the standard also defines a 64-bit format, known as double precision. By jumping from an 8-bit to an 11-bit exponent and vastly expanding the mantissa from 23 up to 52 bits, a double precision float pushes our accuracy from 7 significant digits up to about 16. It drastically reduces those pesky rounding errors on repeating fractions. So, the crucial point here is that while floating point gives us an immense, incredibly flexible range, literally allowing us to calculate the width of a galaxy and the size of an atom on the exact same microchip, it is still strictly bound by physical reality. If an operation results in a number larger than the maximum exponent can actually handle, it crashes right into the overflow zone, which the system just handles as infinity. On the other end, if it calculates a fraction smaller than the bits can possibly represent, it hits underflow, simply dissolving to 0. At the end of the day, we are trying to map the infinite continuous world of mathematics onto a finite grid of silicon switches. It really makes you wonder, as our scientific modeling requires even more staggering scale and microscopic detail, how exactly will future hardware evolve to keep up? What happens to our calculations when they fall completely outside these bounds, or demand infinite precision, challenging the very physical limits of our digital world? The floating point system is an absolute marvel of engineering, a brilliant dance of bits and logic. But it's also a humbling reminder that in computing, every infinity must eventually fit perfectly inside a box. Thank you so much for joining me on this explainer, and I really hope you leave today with a newly found awe for the hardware silently crunching the numbers beneath your code.